This is the first video dedicated to an introduction to organic and biochemistry. It's primarily found in chapter 21 of your textbook, but we only cover the basics in here, and the textbook goes into a little bit more detail. Let's begin. The topics in this chapter include the basics of organic chemistry, some basic nomenclature and naming alkanes that have some branches or side chains, functional group identification, and some basic biomolecule characteristics. Okay, this one topic here is not found within your textbook. And that's okay. Here we go. Organic chemistry, the basics. What is organic chemistry? Organic chemistry is the chemistry of carbon. It is found and really relates to so many things that we use in our everyday lives. Some very common organic compounds, the gasoline in your car. Medicine is organic based. Different types of plastics, perfumes, and of course our food, because our food is composed of a lot of carbs, protein, and lipids. Let's talk about some basic properties of organic compounds. They are mostly covalent, so they're covalently bonded. They primarily involve C, H, O, and N for the elements, which I hope you still remember, are nonmetals. For polarity, they are usually nonpolar, again, because they're composed of primarily nonmetals, and usually those nonmetals are bound to carbons in the same. So similar things around the center means things are nonpolar. When it comes to their melting points and their boiling points, they are low. And again, that's directly connected to the fact that they're nonpolar and covalent. And they are usually very flammable. Think propane, butane, that kind of thing. Now for solubility. Solubility is, how much of something can dissolve into something else. Water, they are usually not soluble in, and that's because water is polar. But other organic solvents, such as like oil or hexane, they are soluble in, and that's because these are nonpolar. Back in the solutions chapter, we talked about how like dissolves like. So things that are polar dissolve in things that are polar, and things that are nonpolar dissolve in other things that are nonpolar. They also can form something called an isomer. And an isomer is kind of similar to an isotope, at least in its prefix. Okay, so isotopes were the same number of protons, but a different number of neutrons, which resulted in a different mass. Isomers are the same chemical formula, but they have a different shape or name or arrangement. Let's do a quick example. So for example, C4H10, which is butane, is 4 carbons and 10 hydrogens. If I draw out C4H10, it can look like this, where they're all connected, and then they're surrounded by H's. And that's one possible structure for this chemical formula. We can rearrange it slightly and change its properties somewhat, and instead have this as our formula. Okay. And again, they're surrounded by H's. That's what these little lines represent. Same number of H's, same number of carbons. But one of these is called butane, and the other one is 2-methylpropane. So they're going to have the same molar mass, but a lot of their other properties will vary slightly. So same chemical formula, different shape is an isomer. Let's talk some of the basic nomenclature properties and rules. These can be pretty complex. We're going to focus only on the alkanes. The name is going to tell us the number of carbons found on the longest chain. Okay. In addition to the number of carbons in the base, it's going to tell us the location of different branches or side chains. And naming can also be used to kind of identify the types of functional groups things have. We'll talk more about those later. The IUPAC nomenclature system is going to be used across the world for uniformity. And there are some prefixes here. Okay. Some of the prefixes are the same as before with the covalents, but some are new. So the new ones are the first four. Meth is the prefix for 1. Eth is the prefix for 2. Prop is the prefix for 3. Bute is the prefix for 4. And the rest of them should look pretty common to you and familiar. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. Okay. So the first 4 are different than the covalents, but the rest are the same. There's a lot of steps that go with these. Let's go over them, and then let's do some additional practice problems and examples. The first step in naming an alkane, and really naming anything, is to identify the longest carbon chain. And putting the word continuous here is not a bad idea. So the longest continuous carbon chain. And this is going to become our base name. This is going to end in A-N-E. Kind of like our molecules and our covalent things used to end in IDE all the time. So for example, if I have a 6 carbon chain, the base for this would potentially be hex for the 6 and then A-N-E for the ending. Okay. We're going to locate side chains, or branches. They get placed in front of the base name and they end in YL. Okay, so they're going to end in YL if they are carbon-based. Okay, and then for example, we could have an extra methyl group or an extra ethyl group. When I have more than one of these groups, I also add in the prefixes di or tri. Okay, and eventually I'm going to also put in a number. So if I take my base hexane from before, and I put a methyl group here. Okay, so this is the extra carbon. Now I'm saying, okay, that carbon is not part of the main chain, so it requires a different ending and has to be labeled. So that is a methyl group. And it's still hexane for the base, so it would be a methyl hexane. You also then have to show the location of each branch or side chain with the lowest possible numbers. So technically I could number this 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. The methyl carbon is on the second or the 5th carbon in the chain. 2 is obviously smaller than 1. 2 is obviously smaller than 5. Sorry about that. So I'm going to rewrite the name with the number 2-methyl-hexane. And then we always separate our numbers with commas if there's more than one, and our numbers and words with hyphens, as you can see here. Okay. We're going to do quite a few more examples on the next slide as well to assist in your study. So there's actually a variety of different ways that these can be shown. Okay, so a variety of different diagrams that are possible, which we'll talk more about on the next slide. You can have your full structural formula, you can have a condensed formula, you can have a line structure or a line formula. That's what this is. Okay, but it's always based around the longest carbon chain. So very often I like to not worry about the H's because they don't affect the name. So I'm going to ignore them. I'm going to circle my longest continuous carbon chain. In this example, it is 6 of them. There are no additional carbons, so all I have to do for this one is label it hexane. In the one over here, they're lines. There's a carbon at every end and every bend in our structure. So this diagram is actually just a line formula of this. They're the same thing, so they would both be named hexane. Okay, let's do one more together and then I'll have you try some. So again, if you don't like that the carbons are missing, you can add them in. Okay, and you're going to want to circle the longest carbon chain. You count up your carbons, you see that there are 6 of them. So the base again here is hexane. There's an extra methyl group right here because it's a single carbon. So this would be methylhexane, and it's actually 2-methylhexane just like it was on the previous slide. Okay. Let's do one more just to be safe. So we're going to come over here. You have to identify the longest chain. It may or may not be the straight chain. Okay, in this one it is. So again, I'm just going to kind of square off my longest chain. My longest chain has 7 carbons. So the base is going to be heptane, because that's representing 7. And then here I have this methyl, or this single carbon, as well as a 2-carbon chain. Normally, when we label our branches or side chains, we label them alphabetically. So the 2-carbon chain is an ethyl group, while the other carbon chain, single carbon chain, is a methyl group. Ethyl alphabetically comes before methyl. So I'm going to number my chain, 1, 2, 3, 4, 5, 6, 7. And I'm going to label accordingly. So my name has a 3-ethyl because the ethyl group over here is on the 3rd carbon. Okay. And then there's actually 2 methyl groups on the same carbon. So this would be 2, 2 to tell someone that those carbons were both on the same carbon in the longest chain. And then because there are 2 methyl groups, we have to say that it's a dimethylheptane. So 3-ethyl 2,2-dimethylheptane would be the correct name. At this time, please pause the video and try to use the examples in the notes to complete the remaining practice problems. Please check your answers. Okay, let's start with this one here. The longest chain is 6. Okay, and then there's an ethyl group right here, and there's a methyl group here. Okay, again, you want to number your chain. 1, 2, 3, 4, 5, 6. If the H's bother you, rewrite them without, and you should have gotten 4-ethyl 2-methylhexane. Let's move on to the one in the middle. Okay, the longest chain is an octane. Okay, then you have this methyl group and this methyl group, and they're on the 2nd and the 7th carbon. Since they're the same, they're going to also need the di, so it should be 2,7-dimethyl-octane. And then finally, the last one, the longest chain is 3, so it's a propane. And then it has 1 methyl group off of it, 1 single carbon group, and it's on the 2nd carbon, so you would say that this is a 2-methylpropane. Okay. Let's continue our study. There are many additional ways to draw structures. Okay, we have the expanded structure and the structural formula, which we've been using, a condensed formula, and a line structure. We will continue to discuss these in our next video.